Hey, good afternoon. Let's start lecture. Okay, so we'll continue on the plane equations in 3D. All right. So we derived the plane equation in 3D in the last lecture, and let's take a quick review, and then we'll look at a few examples. Okay, so this is the essentials for writing down a plane equation in 3D. Okay. So basically what you need is, you need to have a vector. Okay. So you need to have a vector that is perpendicular to the plane. So let's call it n. So let's say the n is given by ABC. Okay, so this is the first one you need. The second one, you need a point on the plane. So let's say I have a point P0 with the coordinates x0, y0, z0. With these two information, then you're ready to write down the plane equation. So the plane is a times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0. Okay, yeah. So this is the plane equation. It's actually quite easy to understand. Essentially, this is how we derived. If this is the plane we're looking for, and the plane contains the P0, and the plane, of course, has an arbitrary point P on it, and P has coordinates x, y, z. At the same time, you have a perpendicular vector n that is here to the plane. Okay. So all I'm illustrating at here now, essentially the n that is here is perpendicular to the plane. In other words, the n that is here is perpendicular to any vectors in the plane, right? So if you connect a vector from P0 to P, and P is an arbitrary point on the plane, so you literally what you get is you get this n perpendicular to this P0 P. Okay. When two vectors are perpendicular to each other, this essentially means n dot P0 P equal to 0. Okay. So if you substitute the vector n, the coordinate P and P0 into this equation, and what you really get is basically this one here. Okay. So that is the plane equation. Good. Okay. So if you have a question asking you for whatever reason, give you some conditions, some basically known conditions, okay, and ask you to derive a plane equation. So you just have to bear in mind the objective is try to find a vector perpendicular to the plane and try to find a point that's on the plane. Then you'll be able to substitute in this equation to get the plane equation. So that's straightforward as that. Okay? Yeah. So that's going in one direction. If the question asking is what's the plane equation, right? And often in time, you're probably going another direction. What happens is you're given a plane equation, and then you'll be asked to do something else, right? So in that particular case, basically, if you're given a plane equation, then there's one thing you need to do before you can actually you wanted to move on any further, right? So if an equation of plane is given, okay, so always bear in mind, if this equation is given, first step you do, you can write down two informations. Okay, you can immediately write down two informations, and these two information, what are they? Number one is what? That's right. You can not a hat. You can write down the normal vector. That's right. Okay, so that's the first thing you need to be able to write it down. And what's the normal vector? If you look at the normal vector here, they are essentially what? The coefficients for x, y, and z, right? Yeah. So for example, if I give you a plane equation, 3x plus 6y plus 4z equal to 1, for example. Okay? Yeah. So what's the normal vector here? Which is 3, 6, 4, right? Okay? Yeah. Now you might wonder, well, what you just write down in here is actually different from this one here, right? Well, they look different, but they are the same. Remember, at the end of the previous lecture, if you expand all the brackets and you move all the constant to one end, to the right side of the equation, and you'll get a constant, right? So that constant here essentially is this one here. Okay? Well, if the plane equation given is in this format, okay, it's in exactly this formatted here, then you're lucky. So you can write down the second information right away, which is what? If you're given it's this equation here, so now you write down ABC normal vector. What will be the second information you can immediately write down? From here, what is it? A point on the plane. That's right, a point on the plane. X naught, Y naught, Z naught, right? Okay, so okay. However, if the equation given is in this format here, okay, it's in this format, so it's different, right? It's different format from this. How would you write down a point on the plane? So maybe let's sit here. Can you write down a point on the plane, on this plane right here? How could you come up with a point on this plane? Excellent. Which one did you set to 0? Whichever one you want. But you can't set all three to 0, right? That's right. That's right. So you need to set maybe just two of them to be 0. And then you solve for the last one. That make sense? Yeah. So that's an easy way to find a point on the plane. And there are infinite number of points on the plane. So literally you can come up with if you're given this one here, there you can come up with all different type of answers. Okay, but you actually wanted to be careful in their selection of the points. Okay, sometimes if you select a point which it turned out to be a very weird number, it could actually give you some difficulty in terms of future following computations, right? So here, let's say for example, you can set x equal to 1, x equal to y equal to 0, and you get your z equal to 1 over 4. So basically, you have a point here which is 0, 0, quarter. Okay, yeah. So that's one way to find a point on the plane. Okay, good. So that's how you basically write down these two information, and then you can carry on using this information for any purpose of the question, right? So just bearing in mind, this is what you need to do. There are two directions always. One is given some conditions, asking you to derive plane equations, and that is given plane equation and ask you to do some some other tasks. Okay, so let's look at some examples that are here. Okay. First one is fairly simple. So let's say if I give you a vector 1, 2, -1, and a plane x plus y plus 3z equal to 5. So give you a vector, give you a plane. So here's a question in here. What is the relationship between v and the plane? Okay. So a lot of questions from now on requires you to sort of visualize the question or the situation here. By visualizing basically means you need to somehow maybe just to sketch something to make your mind to visualize the actual relationships between planes, lines, a dot, a vector, so that sort of scenarios. Okay, yeah. So in this case here, we talk about what's the relationship between the v and the plane. Basically means will this vector be parallel to the plane, or will the vector be perpendicular to the plane, or will it be some sort of other type of relationship? Okay, so that's basically what it means here. Okay, yeah. Okay, so let's think about this one here. So what type of basically operation that you can use in order to determine the relationship between this plane and this vector? If this is the plane right here, okay, and the vector could be maybe directly on the top of it, okay, which that means it's a parallel. Or the vector could be perpendicular, okay, so that's the perpendicular relationship. Or maybe it could also be a kind of relationship with certain angles between this vector and the plane, right? Okay, so that's the three different scenarios. Okay, so how would you determine this relationship in this case here? Right. So all of the future questions here, you actually probably will always fall back to the two type of concept reviewed, which is the dot product or the cross product. Okay, so most of the time you have to use these two operations in order to determine for something. Is that okay? Yeah. Okay. So before we move on, as I suggested, if I give you a plane, right? So what's the first step we can do? We can write down what? The normal vector to the plane, right? Okay. So the normal vector to the plane, 1, 1, 3. Okay. And you can pick a point in the plane, but in this case, it's actually not necessary. So the normal vector is something that we can. It's all we need to determine the relationship here. Good. Okay. So now, if the question asking the vector, the relation between the vector and the plane, what can you translate that question into? Can you equivalent this question into a different type of question now? So instead of looking for relationships between this vector and the plane, maybe you can rephrase that. What would be the relationship between the vector v and the what? The vector in that here, right? Yeah. So, for example, if v is perpendicular to the plane, and what does that mean for v and in? They must be parallel, right? So how would you show that two vectors are parallel? Dot product equal to what?
1.
Dot product equal to 1. That's right. Yeah, you're right. Sorry, I was thinking of a perpendicular situation, right? Yeah. So if v and n are parallel, perpendicular to each other, And what's the dot product now?
0.
0, exactly, right? Yeah. See, that's exactly basically the transformation of the original question to a different description now, right? So let's see. Basically, let's find what's the dot product between these two vectors that are here. Okay? Yeah. So whether it's 1 or 0. So this one dot this one here, which is 1 times 1 plus 1 times 2, and plus 3 times -1, which is 1 plus 2, 3, 3 plus -3, 0. Okay? Yeah. So, as we just discussed, if the dot product is 0, and that basically means this n is perpendicular to the v. So if the v is perpendicular to the plane's normal vector, then that means the vector v must be what kind of relationship to the plane? Parallel. Okay. So that's the idea of how you can translate this question to a different math meaning, and to how you can show that through the dot product, cross product. Okay? Yeah. Okay, so that's an easy one. Any questions here? Good. Okay. So let's look at the second one. This one here is not that difficult, but it's a slightly different type of question now. Okay. So here I want you to find the shortest distance, okay, from a point the point has coordinates 1, 1, 3 to a plane. Okay, yeah, to a plane. So find the shorter distance from a point to a plane. And before you even get started, I always suggest you just illustrate this question. Okay, illustrate what this question is asking you for. So you got a plane at here, and you got a point at here, and of course you're looking for is a shorter distance. So shorter distance meaning you project the s vertically to the plane. Okay, and then try to find this distance d at here. Okay. Okay. There are actually different type of methods that you can use for this question that here. Okay. Yeah. So I'm gonna show you something here, but I want you to think actively. But before we move on, okay, before we start think actively, as I mentioned, okay, whenever you had a question and you're given the plane and you're asked to do something, always write down a few things, actually a couple things that you can write it down immediately, right? Okay, so the first thing you can write it down is what will be the normal vector to the plane. Okay, so which is 3, 2, 6. Okay, and then another thing that we can immediately write it down is we can always find a point on the plane, right? And we always find a point on the plane. So there are infinite number of points. Really, here there's no limitations as to which point that you will choose. Okay, but however, choose a point that is an integer. Choose a point that can literally maybe simplify some of the future computations, right? So in this case, maybe I'll stick to the rules here. You can set two variables, 0, and then pick the other variables. So if I set, let's say for example, in my case, I can set x and z to be 0. Then I solve for the y, right? So 0, 0 for x and z, solve for the y, so y equal to 3, right? So here's a point, okay, on the plane. And if you found a different point, that's absolutely okay. Okay. So that's it. Okay, so you write these two information down, and then you can start thinking, how would you solve for the shorter distance from the point S to this plane. Yeah. Okay, so think about it, right? Yeah. So when you're thinking, and as I mentioned, always relate, okay, your thought to the either dot product or cross product, okay, because those are the tools you will actually be able to use to solve this kind of question. And I'll show you two different methods. Okay. I hate to say this, but I noticed a lot of you guys are sort of chit-chatting when I'm talking. You may not realize I actually can hear that very clear. Okay, so if I can't tolerate that anymore, and you know what's going to happen. So please refrain from talking to each other. Okay? If you have questions, raise your hand. That's fine. Okay, but the chit-chat really is kind of annoying. Is that clear? Okay. Okay, so now you have these things here, right? Think about what would you do. Think about the review, right? When we do the review section in the first and second lecture, and I actually emphasized quite a bit when we learned the dot product in one of the concepts, if you recall that, which is what? Projection, right? Projection. So when you use a vector dot a unit vector, if you recall that, what does that physically give you? If you use a vector dot a unit vector, what was the meaning of that? The geometrical meaning. So A dot B hat, for example. Anybody? Yeah. Projected length. Projected, so to be more precise, projected length for a vector A to which direction? To the B direction, right? Okay, so that's a very important concept. You should bear that in mind. You probably use that in quite a few different type of scenarios to solve the question. So think about this, right? Think about in this question here. Can I use that concept to solve this question in here? So what are we looking for? Shorter distance, D, right? Okay. Yeah. Sure. Okay, you pick a point P, yeah. And then what? Oh, why do I pick a point P? Oh, actually, I don't know why yet. As I said at the beginning of the steps, this is something that you can always write it down immediately, right? You may not use that, but you can put down that information. In this case, actually, you will use that. Okay, yeah. So you will use this point P at here, and you'll use the point P to relate to the hint I just told you. Yeah, David.
If you use the if you make a vector between point P and S and then project it in the n hat direction.
There you go. Right. That's exactly the thoughts. Okay. Yeah. So see, in other hands, was that the same? Yeah. Yeah. So we just said when you use a vector dot a unit vector, you get the projected length of the vector in that direction, right? So this is exactly the thing you can make use of. If you connect P and S, okay, and this is the vector PS, and this is an n, not n hat, but this is a normal vector n at here. So the D at here is basically what? It's basically the projection of the PS in the vertical direction. That makes sense? Yeah. So then everything is so simple now. So then you create the PS first, okay, and that essentially is the coordinate of S minus the coordinates of the P, okay, and so that gives you 1 minus 0, 1 minus 3, and 3 minus 0, Okay, so that's your PS. Okay. And then your D, okay, is basically your PS dot the n hat. Okay, dot n hat. So sometimes this can be a negative number, so you can put an absolute sign just to get rid of that negative number. That's okay. Okay. So that's n hat. And but we don't have n hat, right? So the question here didn't give you the n hat. The question here just give you the n, so which is the vector that you just wrote it down here. So we can normalize this n to find this n hat at here. So that's a simple, yes?
The PS vector is not supposed to be -2.
Oh, -2?
1 minus
Oh, yeah, that's exactly, yes, sorry. Excellent. So that's the type of question actually you will make during the exam, right? You calculate one number or one sign wrong, and then the rest of things will be wrong, right? So good. Make sure to avoid that type of mistake. Okay, so I substituted all the informations into this expression in here, and the calculation should be fairly straightforward, and you get 17/7. Okay. That'll be the shorter distance from the point S to the point to the plane here. Okay. Yeah. So as you can see, this is literally just one expression in here, right? To give you that, the answer. Yeah. But the understanding at here, always remember, the understanding here is based on your understanding that A dot B hat is the projected length of A in the B direction. Okay. But I do have another method here. Okay. So this is a slightly different from thoughts from this first method here. So I'll show you this second method here. Okay. All right. So here's point S at here, and here's N at here. And we're looking for the shorter distance. So let's say, for example, suppose that I drop the S to the plane, okay, and dropping the S to the plane, and that point, intersection point at the point P at here. Okay. So ideally, if you know where this point P is, then the D will simply be the distance between the point P and S, right? Yeah. So that's literally from the geometry, right? Okay. So, but of course, you just have to find the coordinates for the P at here. Okay. Yeah. So PS is perpendicular to the plane. So you just have to find this point coordinates for the P. So I don't know what the coordinate P is, but I can still create the vector PS, right? So then I can create the vector PS. Okay. So using the coordinates S, subtract coordinates for the P. Okay, so that's your PS. Okay, so let's see how do we proceed from here, right? Okay, so we make use of basically available information in here. If P happen to be the point such that PS is perpendicular to the plane, okay, then what's the relationship between the PS and the normal vector N? Parallel. Okay, so if they are parallel, and I want to use a math expression to describe the parallel relationship, then the two vectors must be different by scalar, right? So let's say call it the K at here. Okay, yeah. So they just be different by a scale K. So I have this normal vector N, so substitute normal vector N at here, which is a 3K, 2K, and 6K. Okay. And PS, which is this one here. Good. So substitute this one to the PS. You have basically one side is vector, the other side is also another vector. That makes sense, right? So when two vectors are equal to each other, which basically means the components of the two vectors must be the same as each other. So that gives us 1 minus x equal to 3k and 1 minus y equal to 2k, and 3 minus z equal to 6k. Okay. So that's the first, the relationship based on these two parallel vector. And then we can solve for x. Okay, so x equal to 1 minus 3k, y equal to 1 minus 2k, and z equal to 3 minus 6k. Does that make sense? Yeah. Okay, so now here, please remember, this x, y, z at here, literally, it's the coordinates for the point P. Okay, coordinate for the P here. So point P has a relationship x, y, z relates to the k like this. As we're going to learn pretty shortly, okay, just very soon. For this one here, this is actually a line equation in 3D. Okay, this is actually a line equation in 3D. So we'll see how we can derive a line equation in 3D, but the formality at here, okay, it's basically it's a line equation. Okay. Well, that doesn't really solve the problem, right? Because we're looking for the coordinates of P, so we need to find the actual numbers for the P. But here we only find a relationship x, y, z to the k. So in other words, I need to find a certain value for the k, right? And then substitute here, and then I'll be able to find this x, y, z. Does that make sense? Yeah. So now we think about what other condition that we haven't making use of yet, right? So the P at here, we haven't make use of a condition is what? The point P is where? It's on the plane, exactly. If point P is on the plane, which means if you substitute the coordinates of point P to the plane equation, it must satisfy the plane equation, right? Yeah. Then what is the coordinate for point P? It's this, x, y, z. Okay. So then let's substitute the coordinates of P back into the plane equation, which is this one here. Okay. So let's do that. Okay. So sub point P, okay, to plane equation. So then we end up with 3 times y minus 3k, so that's x, plus 2 times y minus 2k, and that's y, and then 6 times 3 minus 6k, that's for z, and equal to 6. Okay. So now things are fairly clear now. You know, you have one equation, one unknown, which is a small k, and then you can solve for the small k. So you get k equal to 17 over 49. Okay. And then we substitute k back over here. Okay. Now we can get the coordinates, the actual coordinates for this point P. So now we get substitute this one back over here. Okay. At the same time, and then you will calculate the d now. So I'll let you to do the calculation, okay, for the actual coordinates for the P. But then the distance, okay, once you find the P coordinates, the distance will be just the distance between the P and the S vector. That you end up with the same. Of course, you're going to end up with the same answer as the method number 1. Okay. So that's a different way of thinking, right? In terms of getting the shorter distance. Okay. So there might be other actually methods. Okay, it's not constrained just to this first and second. Okay, you can think about if you even could think of any other method, that's fine. Okay. So let's stop here. So let's look at the third one here. Okay, and then we'll call it a day for the plane equation. I'll give you 2 planes here. Okay, so there are 2 planes, and we want to find the angles, okay, between these two planes. So in your mind, you start to visualize, okay, so I have got two planes here, one plane here, so what will be the angle between the two planes, right? So you actually probably want to immediately visualize, okay, so what will be a possible relationship between two planes in 3D? Okay, so if the two planes are on the top of each other, that means they must be parallel to each other, right? Yeah. Or maybe they just collapse with each other, meaning the two planes are essentially the same plane. Okay? Or the planes can be skewed to each other. Then, because planes are literally infinite, extended in space, then there will be an angle between the two planes, right? Yeah. So that's basically what it means. Oh, it doesn't matter if even the planes are parallel to each other. That means the angle between the two planes is going to be 0, right? Yeah. Okay. So in this case here, either way, you're trying to find the angle between the two planes. And actually, I'll show you later, it's actually quite easy to determine whether the two planes are parallel to each other or not. So maybe this is the question here. How would you know the two planes are parallel to each other? Immediately. Yes. Yeah.
If they equally divide out.
Equate.
So if one of them, if you multiplied it by a certain factor, it would equal the same thing.
What are the same thing? Yes, I think you're on the right track.
So if you multiply that by the bottom one by 3,
Mm-hmm.
I don't think it would work in
Yeah,
this case.
not in this case.
But
Okay.
if you multiply it by 3,
Mhm.
you end up with, you could end up with having the same as the first one. If the two of them equal something by a certain factor.
Oh, you're trying to make these two sides the same. Is that what you?
Yeah.
Mm.
If the two sides are the same, if you had a certain factor, you could make the two equal.
You're almost there. So, if the two planes are parallel, not actually, you shouldn't look at this side here. You should look at what? This side here, the normal vector. Okay? If two planes are parallel, that means the two normal vectors to the two planes must be parallel to each other. Then the two parallel vectors must be just different by a scale, right? So then you just look at the coefficients, whether the two sets of normal vectors are a scale of each other, or even just simpler, are they the same as each other? Okay, yeah. So in this case, we're not talking about that scenario, because the first one is 3, -6, -2, and second one is 2, 1, -2. Okay, so they're not scaled by any factor, any integer factor. Okay. Yeah. Okay, so now we can go ahead and try to find the angle between the two planes. Then maybe in this case they're not parallel, so we can probably illustrate slightly different now. Okay. So let's see, that's the intersecting scenario for two planes. Okay, so you've got two planes intersecting each other. Okay. And then here is N1 and here is N2, for example, right? Okay. And we're looking for is this angle between the two planes. Okay. So once I draw it out, I think you probably will find it's quite easy to do this now. If you're trying to find the angle between the two planes, and you can translate the same question into what? To find the angle between the two normal vectors. Okay? Yeah. So to find the angle between two vectors, we can use the geometrical meaning, that dot product. Okay. So that basically you can use the arc cosine n1 dot n2 and n1 n2. Okay. So in this case, you get approximately 1.38 readings. And that's approximately 60 or 70 degrees or something like that. Is that good? Yeah. So that's three different type of questions for planes. Okay, so in assignments, which we'll give out tomorrow, you have some other exercise for plane equations. All right? Yeah. So make sure you do that. Just provide you a little bit of summary at here. Okay, before we move on to the line equation. What will be the typical questions related to planes in 3D? Okay. So I will just write it down. Essentially, I'm not gonna give you examples, solve anything in here, but it's just to provide you some kind of thoughts. Okay. You look at this one, you can actually literally think about it here. So what's the typical questions here related to plane? First of all, there's some easy ones here. Actually, maybe there's the one like the one we just did from the example. What will be a distance from point, okay, to a plane? That's a very typical question. Like the third example, angle between two planes. Okay, so those are basically, this is a kind of question. You're given plane equations, and then you find some informations, right? Some other information. And you could also going the other way is to find plane equations. Okay. Yeah. So here there are really a lot of variations that are here when you're asked to find plane equations. Some are really simple. So let's say you probably will be given a point, okay, and a normal vector. Okay, so this is the simplest scenario now, right? So you got a point, you got a vector. So you basically means the point of a plane, the normal vector is perpendicular to the plane, and then the plane equation. Literally substituting to the formula for the plane equation, you get the plane. Okay, so another scenario, you probably given a point, okay, but instead of giving a normal vector, so let's say you're given another parallel plane. So think about it. Okay, so I have a point on the plane. I have a plane given. That plane is parallel to the one we're looking for. So how would I construct the plane equation? Right. If the parallel plane, this is actually the same as the first scenario. You can get a normal vector from the parallel plane and use that to construct your plane equation. Okay. Another one is actually we did that when we derived the plane equation. So you're given 3 points, and to construct a plane that goes through those 3 points, right? Okay. So if you're given 3 points, so now you can think about it. How do I construct the plane, right? But before you can even solve it, the first thing jumps in mind is, in order to construct a plane, I need a point on the plane. I also need a what? Normal vector to plane. So if I were given 3 points, then I already have points on the plane, so I can use either one of the 3, right? Okay. But I do need a normal vector to the plane. So how do I get the normal vector to the plane from the 3 points? Make a vector to the using the 3 points, and then what? Cross product. Exactly. Right? Very good. So pretty soon we'll learn the lines in 3D. So then here is a connection. So you're given a point and a line, okay, to which, okay, the plane is perpendicular. Okay. So that's another scenario. Now once we learn line, then you will see that but here you will still think along the same direction. So if you're given a point and a line to which the plane is perpendicular, so basically means you already got a point, you still need to strive to find a normal vector to the plane, and that will be able to be extracted from the line given it here, because here it says the line is perpendicular to the plane, right? So that information can come from there. And another scenario, the last may not be the least, is you're given a point, okay, and the line, okay, that the plane goes through. See, so you're given a point and a line. So here's a point, here's a line, and then you're looking for a plane, basically, that goes through this point at the same time is also going through this line. Okay? Yeah. So I won't give you a solution yet because we haven't learned the line yet. But once we learn the line, then you will see how you'll be able to solve. But either way, you need a point on the plane, and you still need to try to find this normal vector to the plane. It's all about how you can find this normal vector here. Okay? Yeah. So that will be the possible scenarios there. Okay? Another type, it's very actually straightforward. Later we're going to look at it. Is when you intersect two planes, and you will see that, okay, the intersection of the plane, okay, of the two planes will give you a line. Okay, give you a line. So basically, what will be the line equation, for example? Okay, so that's another scenario. Okay, so this is all the possible type of possible questions for plane only, or sometimes a little bit related to the line. Okay. And once we finish the line equations, then we have a complete picture of everything. Okay, any questions so far for planes? Okay, good. Okay, so let's continue it here now. Let's continue basically to look at equation for lines in 3D space. Okay. So this is a very general scenario. Now, this is not an equation in 2D. It's not like y equal to kx plus b. This is about finding the line equation in 3D space. As you will see, it actually looks quite different from the line equation in 2D space. Okay, so let's start off by just draw a line, okay, in 3D space. And then I'm going to pick a point on the line right here. So I'll call it x, y, z. So I purposely left a little bit of room in here, okay, after x, y, z. Okay. So what do we want? Of course, you bear in mind what you really want. You want expressions, mathematical expressions for x, y, z, and such that that expression will be able to describe this line at here, right? So that's the purpose. Okay. So what I want you to now think about it. This is think actually slightly in a different perspective. Instead of just thinking of it as a point on the line, so let's maybe for now let's think about this is a moving point along this line. It's a moving point. Not just a line, that's a moving point along a trajectory. Is that okay, right? Yeah. So it just happened that this trajectory is a straight line, right? Okay. So if P is a moving point, then maybe at a certain time moment is here, at another time moment is here, and another time moment is there. Right? So that's the idea. Then, which means the coordinates x, y, z, okay, will be a function of t. Okay. So if I think of P as a moving point, then the coordinates for x, y, z can be thought of as a time parameter t, right? Okay. So now you can think about it is, so we got x of t, y of t, and z of t. Okay. But really what we want is we want to find an expression for the x, for the y, for the z. At the same time, always remember this x, y, z is on the plane. It's on the straight line, right? It's on the line at here. Okay. So literally, I'm trying to look for is, instead of looking maybe for one expression relates everything, maybe I can rethink as of I'm looking for three expressions: one for x, one for y, one for z, and together the x, y, z still describes a straight line. That makes sense, right? Okay, it's a little bit slightly different from the Euro ways of thinking now, right? So I'm looking for three expressions here now. So the three expressions, of course, the notation wise is all the three expressions will be a parameter, will be a function of what? The parameter t. Okay, t at here. So I don't have it yet. I don't have any general expression yet. But just think if you have one, right? If you have an expression here and here, so you will have three equations basically. So these three equations, okay, and this is something new now. Okay, this is basically all in terms of t. Okay, it's all in terms of t, and we can call it parameter t. Okay, it's all in terms of parameter t, and the three expressions which we will give shortly, and we call this parametric equation. Okay, so parametric equation. So that's a new concept here. So we will be able to derive three expressions in this case, and essentially we're going to derive a so-called parametric equations. Okay. Yeah. More general, later you will see that even though I use a t at here, okay, because they're called parametric equation, you can literally exchange this t to any parameters. You can change to s, you can change to whatever numbers, whatever symbols you use. So that's still qualified mathematically as a so-called parametric equation. Okay. Yeah. Okay. So let's look at the derivation for the plane equations at here. So I'll show you two different methods. They're actually quite similar. There is a little connection here. But the first method I derive, more or less I'll relate that to this moving point P, and also to use a very basic physics concept here. Okay, yeah. So let's say this is a line in here, okay, and we're gonna consider a moving point along this line in here. So let's say I have a straight line that goes through this Q0 and Q1. Okay, yeah. So if I rephrase the question, maybe let's say, can we find the line, okay, equation given 2 points? Okay, the line goes through. Okay, so it's pretty obvious. 2 points determining a line, right? And it uniquely determines a line. So you can't have any other lines go through this Q0, Q1. It's going to be the single line go through this Q0, Q1. Okay, so let's see. I give this Q0 as negative 1, 2, 2. Okay, is the coordinates, and the Q1 given as 1, 3, negative 1. So, for example, these are the two coordinates for Q0 and Q1. Okay. Yeah. Okay. So the first method we're going to use is we're going to consider there is a moving point along this straight line. So this moving point, I'm going to call that Q. It's moving at a different time, so it has its own trajectory. Okay, it has its own type of motion. And I'm going to actually define the motion for the q at here. Okay, so if you think about it, you can really have a different type of motion. The q could be moving fast, slow, slow, fast, that type of things, or the q could be just simply moving what at the constant velocity, right? So that's a simple condition. Okay, so let's consider that simple condition here. I'm going to assume this q, okay, is moving at constant velocity. And also we can assume the following things at here. Suppose that at t equal to 0 time moment, this q, okay, is at this q naught location. At a t equal to, after certain duration, capital T, and this q is at this q1 location. At any other time moment t, your q is at q of t. This time, this location, right? So q of t, as the previously noted, is x of t, y of t, and z of t, right? Okay, so those are good now. So those are the consumption assumptions we can make use of now. Okay, so then let's use the physics concept. In physics, basically, if you recall that, what does the velocity equal to? Velocity equal to what? Displacement over time. Good. Okay. All right. So I'll make use of the formula here. Okay. Remember, we're considering the q is moving at a constant velocity, right? Okay. So from q naught to q, this is how much it travels. Okay. From here to here, this is how much it travels after a certain what?
Amount of time.
That's right, t, right? From here to here, this is how much t it takes. And from q naught to q1, how much time did it take? Capital T. Okay. Okay. So let's make use of this. But they should still have the same velocity, right? So from q naught to q, that's your displacement. Remember, this is the vector now. Displacement is actually the vector concept. Divided by the time duration, you get the velocity, which is also a vector concept. And then from q naught to q1, and that's your displacement. And then this is your time it takes to travel that much, and that's your velocity. So these two velocities should be the same, right? Okay. There. So I got all the information written down at here now. Okay. So all I need to do is to substitute the given numbers into this equation in here. Okay. So we're going to substitute what we need to have here into this equation. Q naught we know, Q we don't know, but we can keep the Q as it is. Okay, so the Q has coordinates of x of t minus the coordinates for the Q naught, which is plus y now. Right, Q naught has a -1, 2, 2. Okay, so then you have y of t minus 2 and z of t minus 2. Okay, and then Q naught Q1, you use the coordinate Q1 minus Q naught. So 1 minus -1 is 2, 3 minus 2 is 1, -1 minus 2 is -3. Okay. Okay, so that's what we're going to have after the substitution in here. We still need the divided by the t yet, right? Divided by the t. Small t, okay? Yeah. All right. So now, seems actually clear now. we're gonna multiply the small t to the right side here. Okay, so multiply the small t to the right side. Cool. Okay. So now, if you look at this equation now, so then I can actually derive three expressions for x of t, y of t, z of t. So equate x of t plus 1 equal to small t over capital T times 2, and solve for x of t. So you will be able to get x of t equal to -1 plus 2 over capital T times small t. And y of t equal to 2 plus 1 over capital T times small t. And z of t equal to 2 plus, plus is negative, so minus 3 over t, capital T times small t. Okay? Is that good? So now you see, we end up with the results or set of equation. Basically, it's the parametric equation that we're looking for. So x of t is function t, y of t is function t, and z of t is a function of t. Okay? Yeah. And what's more, okay? And you can actually now look at this one here, okay? Is if I use a different t, okay, if I use a different capital T, and I will get a different number set here. Is that right? Yeah. So for example, right, if your capital T is 1 second, so basically means it takes 1 second to travel from Q0 to Q1, then this equation becomes -1 plus 2t 2 plus t, and this will become 2 minus 3t. Okay? Is that good? And if t equal to 0.5, and we're going to get a slight different now, so this is still -1 here, but this will become 4t, and that will become 2t, and this will become 6t. So now you see, with the different value of a capital T, we got absolutely different equations now, right? So, you know, by looking at the equation here, they're different. Okay, they're not the same. However, what are they describing? They all describe what?
The difference in time.
They describe the different time, but they all describe the same, the line, right? They all describe the same line. So literally, if you forget about the motion now, if you just think of just talk about the line we're looking for, these two here, they actually talking about the same line equation here. Does that make sense? Yeah. But then, of course, this is actually another exercise. Maybe next lecture we'll look at it. But if you think of the physical meaning behind these two, of course they're different, right? They're different because one talks about velocity that actually is faster. This is faster velocity here, right? For moving point along this line right here. Okay? So this is something I actually want to emphasize. Maybe we'll have a example next lecture. Essentially, not just the mathematical expression, but also what's behind that mathematical expression here. Okay. So for example, right? So let's take a second look at it here. So this is how I derived Q naught Q divided by small t equal to Q naught Q1 divided by capital T. Okay. Now if you look at this whole right side here, Q naught Q1 are known. So Q naught Q1 divided by capital T. This is basically what's the physical quantity means in here. This quantity here means what? Velocity, right? That's your velocity, isn't it? That make sense? That's your velocity. So now if I keep looking at it here, okay? Because you're moving down here, so this is your velocity, right? This is your velocity. This is your velocity vector, okay? This is your velocity vector. Keep moving, no change. So this one, this portion in here, this portion is the velocity vector. Okay, and then from here to here, where did that velocity vector go? Okay, so because we separate this expression now, where did this velocity vector go? It went to where? That's right. It went to where? It went to here, right? Can you see that? Okay. Where did it go? All the velocity vector. Remember, velocity vector here is a constant here, right? This is a constant velocity vector. What is a constant velocity? So 2 over t, 1 over t, negative 3 over t. That's your velocity vector. And when we write down the parametric equation, where did it go? It goes to become what? To become the coefficients for the t. Okay. And if you're moving to after giving actual t value, where would that velocity vector now? The velocity vector here is 2, negative 3, negative 2, 1, and negative 3. And where is this one here? 4, 2, negative 3. That make sense? Yeah. You see that this is a line equation, parametric equation, and the coefficient in front of t basically is what? The velocity vector here, right? Yeah. Okay, how about this negative 1, 2, 2? What's this negative 1, 2, 2 here? It's, where did my pointer go?
0.
Yeah, so negative 1, 2, 2 is basically, it's the point Q naught at here, right? The Q naught. And Q naught is a point exactly on the line we're looking for. So you see here, okay. So your plane equation, the plane equation we just derived, has two very important information. The first column here representing is what? Point on the line. And the second column here representing it's the velocity, right? So I'm still calling it velocity, but actually I'll call it actually slightly different, shy away from a physical concept here. But let's still call it velocity here. Okay? Yeah. Does that make sense? And then also you should establish concept now. Okay, I could have different velocity vector, fast or slow, and that basically will give me what? Completely different parametric equation. But behind all the parametric equation, they all describe the same straight line. Okay? Yeah. So that's the basically logical connection at here. Okay? So bottom line is, remember, okay, parametric equation for line, okay, is not unique. Okay, so that's the something you should always remember here. Now let's think about a different way of deriving line equation. But this time, I'm gonna shy away from a physics basically principle or concept. Okay, just purely use mathematical idea. But you will see they are actually the same thing. Okay. So in this case here, let's say I'm gonna try to find the line equation. Okay, going through a point P naught. Okay, so going through a point P naught here. At the same time, okay, and the line, okay, is parallel to a vector V. So that's the second way of deriving a line here. This one here has nothing to do with physics. Okay, it's just pure math concept here. So you have L here, the line L we're looking for, and you have this P naught at here, which is the line goes through. Okay. At the same time, the line is parallel to a vector V. So the V, suppose we know already, so V1, V2, V3. Okay. And what will be the parametric equation for the line L at here? Right? Nothing to do with physics now. Okay? Nothing to do with physics. So we don't have to think about anything like a moving point. Okay? But we can still see, okay, here's a point P on the line. Okay? X, Y, Z. And we need to find this X, Y, Z that describes this straight line L. Good? Okay? So the derivation is actually quite simple. You have the P naught, and then you defined a variable P. Okay, so then we can define ourselves, okay, this P naught P vector. So the P naught P vector is basically coordinates of x of P minus coordinates of P naught P. Yeah. So you get this vector P naught P, right? Okay, that's the first condition you make use of because the line goes through the P naught. The second condition also says the line is parallel to this given vector V. Well, then that's somewhere I actually touched upon in one of the examples that we just finished. If a vector is parallel to another one, then what's the relationship between the two vectors? They are only different by a scale k, right? So we can use a scale k at here to tell the difference. So V is given, and we can substitute k times V. Okay, so that's your k times V vector. And then you have the P naught P vector at here. So equate this with this, and then let's write down three separate equations for x component, y component, and the z component. So we end up with x equal to x naught plus kv1, y equal to y naught plus kv2, and z equal to z naught plus kv3. So this time we didn't use any physics concept here. We just used the math conditions, and we end up still end up with three sets of equation, or we end up with the parametric equation. And in this case here, the parameter we're using is a k at here, right? So literally, your x can be written as x of k, such like that. Okay, yeah. If you give a different value of k, you're gonna get what? You're gonna get different coordinates for this point P. Okay, for the point P. So you substitute different k at here, you get a different coordinates. So if your line really goes from infinite to positive infinite to one end to the other end, infinite to two ends, then your k value can be taken as any numbers from negative infinite to positive infinite. Okay. But sometimes you probably will say, okay, I have a segment of a line. Then the key value will be defined by certain intervals. Okay. Yeah. So that's basically different. It's the same thing, basically, right? It's the same thing, but you see that there's a different perspective looking at these line equations here. Okay? And what's more here, there's one more before I finish it here. Okay. This is one way to write down this parametric equation. So this is a parametric equation, right? Okay. Now maybe I will illustrate this parametric equation just slightly again here. Okay, so this is L at here, and this is a P naught at here, right? And this is a V at here. Okay. Yeah. And then you have your position P on the L at here. Okay. Okay. So if I connect the origin, okay, to P naught, and the origin from the origin to the P at here, is that good? Yeah. So P naught has a coordinate x naught, y naught, z naught. Okay. So P naught has x naught, y naught, z naught. If I connect from here to here, then this red one here, I'll call it R naught. So that'll become the so-called position vector for the point P. Okay? And here you can consider this is the position vector for the point P, right? For the point P. So let's call this is R at here. Okay. So now this is basically R naught is a position vector for P naught, and R is a position vector for P. Okay. Is that good? So why am I doing this? So let's go back to this parametric equation here. Okay, parametric equation. What's on the left side of parametric equation is x, y, z, isn't it? Right? It's x, y, z. And the x, y, z is basically what? The position vector for the point P, isn't it? So I can write this whole left side as the position vector R. And then you have x naught, y naught, z naught, which is exactly what? The position vector for the point P naught. And what does that equal to? It equals to the R naught plus this whole chunk, which is k times V. Okay, see that? So now this one here is a much abbreviated or shortened equation representing this line, straight line equation in 3D. Right? Now this one is called vector equation. Okay, it's called a vector equation. So we'll actually we'll deal with this one here quite shortly, maybe after this month, when we're doing with vector operations. Okay. So just heads up, assignment number 1 will be given this Friday. Okay, you're gonna have 1 week to do. We have a Dropbox on the first floor. Okay, so please drop it off, but make sure you write down your student name, number, and the tutorial section. Okay, the tutorial section.